so right on top.
Alright. Okay, so like I said, the first thing we're going to do is we're going to compare two different types of pipetters. And these aren't actually the names that I'm just kind of going along with what the name is in your books that you read and stuff, which is an or automatic pipette versus a graduated pipette. The automatic pipettes are frequently called Eppendorf pipetters. I forget what the other pipettes. Yeah, there's some, maybe stereological pipettes actually. But we'll go by what's in the book. Yeah. Okay, so still on screen? Yes. Okay. Comparing. Automatic versus graduated pipettes. Let me ask you something. You guys all read this. Are we comparing these two pipettes in terms of their accuracy or in terms of their precision? Remember that's close. Yeah, exactly. That, by the way, is my favorite teaching joke. I never tire of it, and you will hear it all year long. So I'm just fair warning right now. And I love it when students lob me that opportunity to use that cheesy joke. Okay, so yeah, no, we are comparing accuracy. Okay, accuracy, remember, is how close something is to the real, to the quote-unquote real value out in the world. You know, today we're trying to dispense half a milliliter of liquid. Okay, and so there is, you know, a hypothetical perfect, spot on to infinite significant figures, half a mil. Okay, and how close are we going to get to that? Imaginary, idealized, perfect value. Okay? Precision is how well you can replicate what you're doing. So the example we love to use is like if you're shooting at a shooting target, yeah? Accuracy is how well you hit the bullseye. Precision is how clustered, as the gun people say, how clustered your shots are. Okay, if your shots are, you know, right on top of each other, but totally off the bullseye, that's high precision, low accuracy. All right. So, which is more accurate? Okay. All right. So here is our strategy for how we're going to do this. Okay. What we're going to do is we're going to dispense out a volume. We're going to dispense out that half a mil from the graduated. We're going to dispense out half a mil from the auto pipette. Okay. And then we're going to weigh them using the same balance. Okay. Now the balance might have some inaccuracies associated with it. Although on the first approximation, mass, you can usually obtain mass much more accurate than you can volumes. To the first, you know, that's kind of a overgeneralization, but in general it's true. But nonetheless, it wouldn't even matter because we're going to use the same balance any time. So any problems with accuracy on the balance should be controlled for because we're using the same one. So we're going to dispense out that half a mil, we're going to weigh it, and then we're going to come up with the density, right? The density is just the mass over volume, okay? And the densities of the liquids that we use, water and hexane, those are known. So we can, I believe they're in the Pavia book, and they're also on the internet. Okay, so you can look at that. All right. He's not going to stop.
It's okay. It's kind of a problem.
Oh, wait till you see him. And he really wants to see you guys. I'm so sorry. His class just is on a break now, and he doesn't have this. And so he won't stop. I'm so sorry. 2 minutes. Using the same balance. Okay. All right, and then calculate the density. Okay, grams per ml is the most common way of expressing density. And compare to literature values. Okay. And I believe in the worksheet I even had to do like a percent difference to see which one has the lower percent difference. Okay. Okay. I do it just a little bit different, or I recommend that you do it just a little bit different from how it's described in the book because it'll go a little bit faster. Okay. So in the book, it just tells you to use one of the conical vials. And I should show you what a conical vial looks like. These guys are the conical vials. Okay, they got threads on the top, so you can put on the top. Yeah, and there's a 3 ml and there's a 5 ml. And what they recommend in the book is that you you just use one of them. I think it's the 3 is what they recommend you use. I recommend that you use both, and you do it in the order or the way I'm going to show you here. That way, you'll have to do less weighing. Okay. Okay, so one thing that I want to emphasize right away is that you know, all semester long, you're going to have either a conical vial or sometimes you'll have what's called a round bottom flask, and you're going to have chemicals in it. Okay, and then you're going to be moving around the lab. All right, whenever you do that, you want what we call a secondary container. Basically, it's just a regular beaker, not an Erlenmeyer beaker, but a regular beaker okay, where this sits in it. And pick one that's appropriately sized, yeah? So a small guy like this, you might pick a 50 ml beaker. That way it can't tip over, okay? This thing, you know, super easy to accidentally knock it over, chemical spill all over the place. So always have a secondary container, okay? All right. Always use beaker / secondary container. Okay. I think your book actually recommends using the tops. So these are the tops to the conical vial. This little blue nut, and then these little kind of rubber / Teflon. I wouldn't use them. The reason for is that if you mess up which one you used, they're not very consistently weighed. Okay, so you know, these two are not going to weigh very accurately or very consistently. Okay, so I just would avoid. Then you don't have to remember. Oh, shucks, was it this top that I used, or was it this insert that I used? I wouldn't use either of them. And as long as you don't, the only downside to not using them is evaporation of the liquid that you just put in there. And that's pretty slow, unless you set it there and go eat a sandwich and then come back. You know, you're going to be okay. All right. Okay, so this is how I would recommend you do it. Okay, so you got both your you got both your 3 ml and your 5 ml. Okay. 3 ml conical vial. 5 ml. All right, I would take each of those. And step 1, get the empty weight. Okay? And write it down for each of those. Okay? And then what I would do is we'll do both pipettes. We've got the auto pipette and we've got the graduated pipette. Do them both with hexane first. Okay? Now the reason why I suggest you do hexane first is hexane doesn't stick to glass very easily. So after I'm done doing this, I can pour it into the hexane waste, which is back there in hood 3 next to Aaron. Okay? I can put a paper towel in there, roll it up a little bit, put it in there, and now that pre-weight that I had will still be good. Okay? If you put water in these, all right, you can sit there with a paper towel all you want. There's still water that is adhered to this and change the mass of it. Okay? So if you do the hexane first for both of them, then you don't have to go get a second empty weight. Okay? All right. Step 2. 0.500 mLs of hexane. With graduated. Like that. Okay. So use the graduated pipette and put 0.5 mLs into the 3 ml conical vial. Okay. It wouldn't actually matter if you used the graduated with 5 ml and the auto with it, but I just chose one way to describe it to you. Okay. Then weight it full. Okay. So you put in the 0.5 quart to that pipette. Clean and dry. Okay. And then over here, 0.500 ml with auto. 8. Repeat. 2 to 4. But with H2O and grad pipette. Okay? And then 9. Repeat. 5 to 7. But with auto P and H2O. Okay, does that make sense? All right. Okay, a couple things. I know I made this, wow, I really explaining this in great detail. For some reason or another, students have gotten a little bit mixed up on this in past years. They end up getting, I don't know, 8 values instead of the 4 values that are prescribed here and stuff. So I came up with this new schematic picture to try to work with that. Okay, a couple things on how you operate these guys. I can't remember if you use this in Gen Chem lab. You'd think, being that I just taught both of those this summer, I would know, but I don't. Okay, so and I did mean to point out when you're using the auto pipette, it doesn't actually list milliliters. Okay, it lists microliters. So if we want 0.5 milliliters, how many microliters is that? 500. Yeah. Milli is 10 to the negative 3. Micro is 10 to the negative 6. So there's actually 1,000 microliters in milliliters. So this is 500 microliters. All right. And so, like this guy right now is listed. It shows 1,000, so that would be 1 milliliter. Nope, we don't want that much. We want, so we'll turn this guy down, and we'll go down to 500. Okay. Now the way you use it is you depress this. Now there's two sort of stopping points on a pipette. Okay, you can you press it down and you feel resistance. Okay, if I now use force, I can push it down even farther. Okay, we don't do the second thing till the end, till we're dispensing. Okay, so when we're sucking up, for lack of a nicer way to put it, we only go to that first stopping point. Okay, so out of the liquid, I go to the first stopping point. I put it in the liquid. I don't just release it like I'm letting a cork go or whatever. I smoothly pull it up. That way I'll avoid bubbles down here at the tip of my pipette. Okay, and then I move it over here. I put it I squirt out into my conical vial, my hexane or my water, whatever it is. Okay, and then to get that last little bit that's stuck in the very end of that through capillary action, I'll give it that extra little squirt. Okay, all right. And then, let's see, so what are we doing? Yeah, so you should only have to do a pipette or a tip switch once, okay? So you'll do the hexane, and then you'll do the water. And you should switch tips when it comes time to do the water. And the way you do that, there's a little button right here, basically. You just push that, and it kicks this guy off, okay? One thing in general about all pipettes, and students always have trouble with this, you always want to use any kind of pipette, auto, graduated, or disposable pipette, which we'll use a lot this semester. You always want to use pipettes straight up and down or vertical, never horizontal. What happens is students say, oh, I'm starting to dispense too much, I better do that. And that messes you up on so many levels. First of all, these work actually better. They stop things from dribbling out when they're vertical. When they're horizontal, they tend to leak more. Okay. Second of all, when you do this, then the liquid starts to go up into the mechanism of this guy. Okay. And that can ruin these. These are actually shockingly expensive. It can ruin these, and then it can also contaminate the next thing that you use with this. Okay. So again, that's true of all pipettes, including the disposable pipettes. Okay, so that's how you use that guy. Now we want to use this guy. a critical mistake you don't want to do whenever you're inserting glass into something, you got to be careful. This is an injury I have seen at least 5 times in working in laboratories. You don't want to hold it back here, okay? And as a general rule of thumb, if you need to use muscle with glassware, if you need to tense up at all, you're doing something wrong. Okay, you should never have to use muscle because you can cut yourself pretty bad. So I grab it at the end here, I put it in there, I just give it a little bit of twist. I'm not trying to lock this thing in there, okay? Give it a little bit of twist, it's good to go, all right? You grab it back here, and I put a little force, what happens? It snaps. And which way is this hand headed? Now that I have a glass dagger in this hand, which way is it headed? Towards the other hand. And I've seen 2 people impale themselves through the hand, all the way. Glass comes out the other hand, and they go to the hospital. Help me. One guy had to have surgery to reconstruct the nerves in his hand. So, anyway. That's a place we want to be cautious. Okay, so we put that guy in there, and then this guy we stick down in, and then we start rolling him up. Okay, and get yourself, somewhat familiar here with how this guy is designated. Okay, so it actually sort of goes in reverse. So there's 1 mil is at 0.9, or I'm sorry. 100 microliters is at 0.9, 0.8, 0.7, 0.6, 0.5, okay? So you go up that way, all right? And so you roll it up, and then you put it over to the conical vial, and then you roll it back down. Okay? Pretty easy, all right? While we're on the subject of pipettes, I just want to finish one more thought. Let's see if I can, yeah. Which one? There used to be another part to this lab that we don't do anymore. It was calibrating these disposable pipettes, and I didn't feel it was worth the time that we spent on it. But these are disposable pipettes. There's going to be a lot of times, like in this lab, when we're rinsing off our aspirin after we synthesize it, it says put in 3 mil. There's a lot of time in organic chemistry, and you'll grow accustomed at knowing when, where you don't need to sit there with a graduated cylinder looking at a meniscus to get 3 mils, okay? You just need about 3 mil. 3.5 ain't gonna hurt you, 2.5 ain't gonna hurt you, okay? With these graduated pipettes, if you give it one squeeze, it depends on the type of bulb. So this is a 1 mil bulb, believe it or not. There are 2 mil bulbs. So I squeeze it, I put it down into the water, I suck up. I don't do this, because then it goes down into the bulb, all right? I keep it upright, and then I push out my liquid. Okay. Make sense? So, if I wanted 3 mils, boom, 3 mils, nice and fast, okay? One thing I also forgot to mention is, whenever you're dispensing liquid, you've got, here's your supply liquid, and here's where I want to dispense it. Always have those close to each other. Don't travel across the world to dispense, dribbling as you go, okay? Always put those things right next to each other. It's better technique, okay? Make sense? Any questions about pipettes? All right, that's it for pipettes. Let's discuss aspirin synthesis. All right. I think the mask thing is going to be good for you guys because it's going to make me work on doing short pre-lab lectures before I pass out. If I do, please wait me. Don't just go home. What was I going to say before I start out? Yeah, okay. All right, in general, we're going to do this pretty much just like it is in the book. I know what I was going to ask you. Have you guys talked in Dr. Morgan's class, and you've only had 2 lectures, right? So he probably hasn't talked yet about skeletal structure. right? Okay.
A little bit.
A little bit.
Okay, awesome, awesome, awesome.
We were
Has it-
have like assignments due
Oh, okay.
about skeletal structures, but
Oh, okay. Yeah, yeah. He's a serious guy, so he's, yeah, hit the ground running for sure, but you're gonna learn a lot of chemistry. The functional groups, does that mean anything to you guys yet? Okay, well, we'll do. All right, real quick, the Cliff Notes version of skeletal structure is there's just too many carbons and hydrogens to draw C's and H's all over the place. It takes way too long. So, 2 rules to skeletal structure, or 3 rules. Any place 2 lines come together at a bend, that's carbon. We're just not writing it, okay? So we don't write in the C's and H's, we just abide by that. Anytime 2 lines come together in a bend, that's a carbon. Anytime a line just ends, like out in space, that's a carbon. Hydrogens are not written in, you just assume there's enough there to explain the formal charge. Now, that's a little bit awkward way of putting it. Usually, how many bonds does carbon like? Likes 4 bonds, okay? Most of the time you're going to be looking at neutral carbons. Neutral carbon, neutral carbon, okay? If it's neutral, that means it's got 4 bonds somehow. So there's the ones that are actually drawn, and you count them up and go, okay, there's 1, 2, 3 bonds that I see drawn. So where's the 4th? It's a hydrogen and it's not drawn in. So there's you always assume there's enough hydrogens to explain. He's 7, so like, what's a critical reason to call daddy and what's a not so critical reason to call daddy is not very clear to him yet.
Honestly, I would just be excited to want to talk at that age.
you're right.
What's that?
At that age, I'd honestly just be wanting to use the walkie-talkie.
Yeah. Well, I got to my office just in time to see him stuffing all his Nerf guns into his backpack, heading out to go. He loves the lab staff here, so he's going out to try to get them to have a Nerf gun war with them, despite the fact that they actually have a job. So, rolling the halls. God help us. Okay. Let's see. Am I still on screen? I'm going to make sure of that. All right. So, synthesizing aspirin, or otherwise known as acetyl salicylic acid. We're starting, the starting material we use is salicylic acid. When we convert it into aspirin, it's acetyl salicylic acid. Okay, so okay, how many carbons are on, that's salicylic acid, how many carbons are on salicylic acid?
9, 8.
Okay, lots of answers, and just not quite the right one yet. 7. Yeah, there's 7. So any place 2 lines come together? Yeah? 1, 2, 3, 4, 5, 6, and then 7. Okay?
Okay.
This what's it?
Because at the end of the line, there's with the OH, it's not a carbon between OH, just
Maybe I
the
should specify that.
Oh.
So line comes out and ends in space, but there's already an atom occupying that position, so it's not a carbon. Yeah, no carbon, that's just an oxygen, oxygen, oxygen. Yeah. Okay, so 7. Everybody see it? Okay, great.